Welcome back to Mr. Hassan's Maths channel. I'm now answering question number 9 from the January 2010 C3 Edexcel paper. This is from the GCE paper, and this question here is related to the new P3 syllabus, and it's all about exponentials, logarithms, and also graphs. And the reason I'm actually answering this question is really to do with 9 part 2B, where it's asking us to find the range of this composite function. Okay, so this is something that's quite a rare type of question, but it's kind of coming up a bit more often. I've seen it in some of the new UK type of questions, and I'm just making sure that we all understand that concept. I also sent a letter to the examining board asking, is this something that is going to, still examined? And they did mention that, yes, they could examine such a concept of how to find the range of a composite function when you know the domain of both the functions that it comprises of. So that's the main reason I'm answering this particular question, and I've chosen this question. Now, let's start with, to be complete, to answer the whole question. So we start with 9 part 1a. This is about solving this equation, this log equation, log to the base e, which we know is ln. So we're going to solve this equation. So an equation like this is kind of already set up for us. And what we have to understand is ln is just a name for the log of the natural number, which is e. So basically ln is just another way of writing, okay, for example, the ln of x is the same as saying log to the base e of x. That's all it means. Same thing, right? So this means log to the base e of 3x minus 7 equals 5. And we know from the laws or the understanding of what a logarithm is, if I know that log to the base a of b equals c, I can rewrite this in the form of a index form. Okay, I can rewrite this in index form. And if I write this in index form, it's going to be, this is the base, a is the base, c is the power, and b is the result. So this can be rewritten as a to the power of c equals b. So as we know, this is log to the base e. This can be rewritten as e to the power of 5. E to the power of 5 equals 3x minus 7. Okay, because remember, this is the same as saying log to the base e of 3x minus 7 equals 5. So e to the power of 5 equals 3x minus 7. And now we have to find the solution to the equation, meaning we've got to find the value of x. So we've got to just rearrange this to make x a subject. So I can add 7 to both sides and divide by 3. And that will leave me what x is. So we can say x equals e to the power of 5 plus 7 over 3. And there's our answer. They want it in exact form, so we don't round this or find the decimal value of this. We leave it in this exact form in terms of e. Okay, in terms of e. So there we have our answer to this question. All right, now that's part A. Part B is a similar type of question in terms of it's to do with exponentials. Now this question is we have to do a bit more work to find the solution for it. In this question, we're told we have to find x, and we've got this kind of like product of these two numbers in index form with x both in the numerator, in the index, in the power. Now we want to release the x's from the powers. All right, so we could do this. We could actually take log to the base 3 if we wanted to, or we can take log to the base e. I'm going to take log to the base e as we're dealing with P3 and we have an e there. I'm going to take the ln of both sides. So I'm going to take the ln of one side. And when you take the ln of one side, you must do the same to the other side. Just like with any equation, when you do something to one side, you do the same thing to the other side. So this is going to be equal to ln 15. Now I'm going to use the laws of logarithms. I know that when I have the log of a product of two terms, I can separate this into the log to the same base of the sum of those separately. Okay, so ln a plus ln b is the same as ln of a times b. So I can split this up into the ln of 3 to the power of x plus the ln of e to the power of 7x plus 2, and that's equal to the ln of 15. Now I can release these x's from these powers using the power law. We know that the log to the base a of b to the power of c can be written as c times log to the base a of b. Okay, this is the power law. If you look at some of my P2 videos on logarithms, you'll see some of the explanation for these rules. Okay, so now this can be written as x times the ln of 3, and this can be written as 7x plus 2 times the ln of 3. Now, we know that the ln of e. Now, we know that the ln of e is equal to 1. Okay, because we know that the log to the base of something of itself is equal to 1, because this to the power of 1 is equal to itself. So log to the base e of 1 is equal to e, right? So if you have ln e is equal to 1. So this will be 7x plus 2 times ln e. We don't have to write the ln e because it's equal to 1. And that's equal to ln 15. Now what I'm going to do is I'm going to isolate the x terms on one side. So I have x ln 3 plus 7x equals ln 15 minus 2. Okay, this is separate from that. And then I can take x as common in these two terms. So I have ln 3 plus 7 equals ln 15 minus 2. So then I'm going to say x equals... Now what I'm going to do, I'm writing this as minus 2 plus ln 15, just to make it very clear that this 2 is not part of this ln L. Okay, so minus 2 plus ln 15 over, and I'll put this as 7 plus ln 3. I just like to write it the other way around, so it's very clear that the 7 has not got anything to do with being inside the ln function, separate from it. Okay, so this makes it absolutely clear. So that is our answer, and again, we were asked to find the exact solutions. So I'm not going to now find the value of these. I'll leave it exactly as it is. And there's the answer to part B of part 1 of question number 9. Okay, so that's just using some of the laws of logarithms to solve these equations. Next, we have 9 part 2. And we're given these two functions. One of them is an exponential function. The other one is a ln function. Okay, and we're asked to find the inverse of function f and state its domain. Now, one of the things that is very important to realize is e to the power of 2x is the same as e to the power of x all squared. Here, like when you have a to the power of m raised to the power of n, you multiply the powers. Okay, so this would be like, that's why it's e to the power of 2x, right? But e to the power of x squared is not the same as e to the power of 2x, because this is not the whole thing squared, it's just the x part squared. So they're not the same. So don't confuse these two. Don't confuse this and this. These are not the same. Don't confuse this and this. They're not the same. These are not the same as each other. Okay? This is only the x squared. This is the whole thing squared. Okay? There's a difference between this and this. See, e to the power of x squared means e to the power of x times x. But e to the power of x all squared means e to the power of x times e to the power of x. That's why we add the powers to get 2x. Right, so they're not the same. So be very careful about misunderstanding that. So e to the power of 2x plus 3, okay, this is a function which is a, if we think about, now we want to find the inverse of this function. So let's first find the inverse. Now, the inverse of a function is found by first, we'll name it y. So that's y equals e to the power of 2x plus 3. The 3 is not adding to the power, it's adding to the whole thing. And then we swap the x and the y around. So we have x equals e to the power of 2y plus 3. And then we try to make this y the subject. So I'm going to make this y the subject. So I'm going to first subtract 3 from both sides. So x minus 3 equals e to the power of 2y. And I want to release this 2y, or the y from this 2y from its power. So I'm going to take the ln of both sides. So you have ln of x minus 3 equals, and that's going to be the ln of e to the power of 2y, which will give you 2y times ln e, which is going to be just 2y. Okay, if you take the ln of e to the power of 2y, that becomes 2y ln e, and that's just 1, so it's just 2y. So that's the same as when you take the ln. Once you've taken the ln of both sides, okay, that becomes 2y. So I'm taking the ln of this side and the ln of that side. So then we can say, therefore, y is equal to ln of x minus 3 over 2. So we can say, therefore, that the inverse function for f is equal to the ln of x minus 3 over 2. And we have to state its domain. Now, one of the things we should realize is that the domain of the inverse function is the same as the range of the original function. So we can say the domain of the inverse function, okay, is the range of the function f. So what is the range of function f? So let's have a think about that now. I'm going to make a little sketch up here. Okay, so now remember what I was saying before. This is e to the power of 2x, not e to the power of x squared. They're not the same thing. Not e to the power of x with just the x squared. So over here, basically what we have is the x values. Like for example, when x is 0, okay, then you're going to end up with this being e to the power of 0, which is 0 plus 1, which is 4. So it's going to go through 4 here. And e to the power of 2x, if it was on its own, okay, when x is negative, this still will be, it will be e to the power of, like when x is negative 1, for example, this will be e to the power minus 2. So it's going to be something which gets smaller. So it will have an asymptote, all right? So it's going to be kind of like e to the power of x, okay, but just slightly more pronounced on this side, okay? But it will go down to have an asymptote at 0. Okay, so the asymptote would be at 0. That's where it wouldn't touch. If it was just e to the power of 2x, it would be like this. It will go through 1 here, and that would be the asymptote. Now, because this has an asymptote at y equals 0, this asymptote is going to be raised by 3 units by this plus 3, because it's like you're adding 3 to the whole function. So the asymptote is going to go up to 3. So it's going to look like this. So you're going to have an asymptote at 3, all right, at y equals 3. And the graph will look something like this. Going to go through 4 and it's going to go steep. This is y equals e to the power of 2x plus 3. So we can see that its range starts from just above 3, never touches y equals 3. And remember, the range is all the values you can take in this direction, going up. Okay, so the range is all the values you can take in this direction here. Okay, so this would be its range. It's a bit big, but no problem. So the range starts from just above y equals 3, and it goes on forever. This goes on forever, getting higher and higher and higher exponentially. So we can say that the range is y is greater than 3. Y is greater than 3, not equal to, because that's the asymptote. So therefore, if that's the range of this function, then that means the domain of the inverse is going to be x is greater than 3. That's the domain of this inverse. And we can see that when we look at this, okay, we know that that must be the case, because if the ln of 0 is undefined and the ln of anything that's negative is undefined. So this is only defined when the value in this bracket is something positive, okay? And it's positive when x is greater than 3, okay? It can't even be 0. Okay, so that's the domain of this function. All right, so that's part 9, part 2, part A. Now for part B of this. This is where we are going to be dealing with the range of the compound of the composite function. So we're going to have a composite function of f and g together. So basically, f of g means where you take the function f and you replace the x in function f with what g is. So you put g inside f. The function g goes inside the function f. So this one has to go inside there. So basically, we're finding f, okay, of g. So ln of x minus 1 is going to go inside this function. So wherever you see x in this function, you're going to replace it by ln of x minus 1. Okay, so that's going to be e to the power of 2 times, instead of x, ln of x minus 1, and then plus 3. That's fgx. Okay, now this can be simplified because here we have e to the power of ln of x minus 1 squared. We can use the power law. And then what we can do is we can understand that this is the same, okay, as just x minus 1 squared, because you have a function inside its inverse. Okay, so for example, if I said to you that y equals e to the power of ln of x minus 1 squared, and we want to find what we want to, rewrite this in another way, I can take, in this case, what I can do is I can take the ln of both sides. If I take the ln of this side, I have ln y equals, and if I take the ln of this side, okay, then I'll end up with ln of x minus 1 squared, because if you take the ln of this side, you'll have ln of e to the power of ln x minus 1 squared. You bring down the ln of x minus 1 squared, and you have ln e. Ln e becomes 1, so you're left with this. So if ln y equals x minus 1 squared, that means y must be the same as x minus 1 squared. Okay, so y, which is all of this, is x minus 1 squared. So this is the function fg of x. That's the expression for the function fg of x, x minus 1 squared. Now, what is the range of this function? Now, this is where we have to think about a little bit. Okay, so fg of x is where you're going to put g inside f. Okay, we're going to put g inside f. Now, g has a domain, x is greater than 1, all right? And the range of the function g, okay, the range of this function g, if we think about it, is going to be what? We know g of x is equal to ln of x minus 1. And that's what's going to be put into the function f. So what goes into f is the output of g. Okay, what goes into the function f is whatever the output of g is. Now, what is the output of g? Well, let's have a look. Okay, what is the range of this function? The output. Now here, they've told us that g is limited in its domain to all x values greater than 1. If we think about the function ln of x, it looks like this. Okay, this is 1. All right, now ln of x minus 1 is like a translation of 1 unit to the right. Just do that too quickly. Okay, it's like 1 unit to the right. Okay, so if you transform this 1 unit to the right, you end up with this being 2 here. So this is ln of x minus 1. All right, now there's an asymptote that has also moved. The asymptote was, okay, the asymptote was, was here. It was the y-axis, that was the asymptote, x equals 0. Okay, because it can never equal 0 what's inside here. But the asymptote has moved to 1. Okay, so the asymptote is x equals 1. Okay, and that's the reason why x is greater than 1, because if it was equal to 1 or less than 1, it would be undefined. So now, what is the range of this function? Even when x is greater than 1, the range is all real values of x, as we can see from this very clearly. It's all real values of x. Okay, the range is going to be from negative infinity to positive infinity. Okay, the range, this is going to go down forever. This is going to go up forever. So the range of this function, the range is y is greater than, y is basically all real numbers. All real numbers. That means, okay, the input of function f is all real numbers. Okay, so for fg of x, okay, the range of gx is y is greater than, or y is an element of all real numbers. Okay, therefore, the domain of fx, when you have this composite function, is x is all real numbers. Okay, so therefore we can say that the range of fg is y is greater than 3. Okay, it's the same answer that we got here. Okay, it's the same answer. It's the range of this function. Okay, the range of this function is y is greater than 3. So it's going to be the same thing here. Okay, because what we can put inside the function f is all real numbers. If we can put all real numbers inside of f, then this would be the range of this function. Okay, so there's the answer to part B. Okay, so it's important for us to understand how to think about finding the range of a composite function. You look at what function goes inside the other. In this case, g goes inside f. What is the output of g? That will be the input of f. The output of g is all real numbers. Therefore, the input of f will be all real numbers. Okay, so the range of g becomes the domain of the f when we have f and g as composite. Okay, so there's the answer to this question. I hope that was clear. Other questions from this paper, if I get to answer them, will be in the playlist that appears in this region here. Other questions to do with range and domain and also exponentials. So I'll put exponential logarithms in this playlist, and I'll put the functions and graphs in this playlist. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.